Section 8.4 is right triangles. Trig functions in a right triangle. For an acute angle A, this is super important. It has to be an acute angle. What's an acute angle? Well, an acute angle has to be less than 90 degrees and greater than 0 degrees. An acute angle is bigger than 0 and less than 90. For an acute angle A in a right triangle, has to be a right triangle. For an acute angle A in right triangle ABC, the trig functions are as follows. So before we get into the trig functions, notice in this right triangle, angle A, the side opposite of it, is side A. Sides are lowercase letters, angles are uppercase letters. Opposite angle C is side C. Opposite angle B is side B. That is not a coincidence. So we're focusing right now on the acute angle A. So let's talk about different parts of this triangle before we get into the trig functions. Opposite 90, this is the 90, opposite the 90 is always called the hypotenuse. The two sides that make up the 90 degree angle, those are legs. So every right triangle has two legs. Relative to the acute angle you're given decides on which leg you have. For example, if we're starting with angle A, side B is the adjacent leg. Side A is the opposite leg. If we were to start from angle B, that was our acute angle, then we would switch these two. We would switch those two because A would be the adjacent and B is the opposite. An adjacent leg is a leg that touches the angle. An opposite leg is a leg that does not touch the angle. Notice no matter which angle we choose, A or B, I guess I can't pull off what I was trying to pull off there, the hypotenuse doesn't change. It is opposite 90 every time. The definition of sine of an angle, S-I-N, is the opposite leg over the hypotenuse. In this triangle, the opposite leg, once again, is A. The hypotenuse is C. That's why this says A over C. The next one is cosine of an angle. That's the adjacent leg. This is the adjacent leg over the hypotenuse. C is the hypotenuse. That's why it's B over C. Tangent of an angle, in this case angle A, is the opposite leg over the adjacent leg. That's why it is A over B. Some things that need pointed out. Universal things that are of mucho importance. These three things are called trig functions. Immediately following a trig function, every time, is an angle. It must be an angle. Cannot be anything else. The trig function of an angle always equals two sides of a triangle written as a ratio. Excuse me. You don't necessarily have to write all this down, but you have to know that after a trig function is an angle, and it always equals a ratio of two sides of the triangle. Now I'm hoping that when you were in geometry, you learned all this. If you haven't, well, I'm teaching it to you like you've never learned it. There are three more trig functions that I'm sure you haven't seen before. This is cosecant, secant, and cotangent. tangent. If you've memorized the first three, sine, cosine, and tangent, then the next three are just the reciprocals of the first three. Reciprocal means that you take a fraction and you make the top the bottom and the bottom the top. So what do I mean by that? Sine of the acute angle is opposite leg over hypotenuse. Cosecant is the reciprocal of sine. It is the hypotenuse over the opposite leg. Similarly, cotangent is the adjacent leg over the hypotenuse. Secant is the reciprocal of that, is the hypotenuse over the adjacent leg. Lastly, tangent is the opposite leg over the adjacent leg. Cotangent is the adjacent leg over the opposite leg. Well, how do you remember which one goes with which? Well, one of these is organic, the other two are not. Tangent and cotangent are organic. They're both tangents, one's got a co, one doesn't. It'd be nice if sine and cosine were reciprocals, and secant and cosecant were reciprocals, but some idiot who invented this chose not to do that. Here's how I remember it. Secant, the last letters, C and S, backwards, is the same letters the backwards for cosine. Cosine has a C at the beginning, S at the end. Secant, S at the beginning, C at the end. And then how I remember sine and cosecant, they're the only two that are left. Kind of lame, but that's how I got it going on. This little fella right here is an ancient Indian chant. Long time ago, Chief Wahoo was sleeping one night late in his little teepee, and he thought he heard a noise outside, and he got up to check it out, and when he ran out, he just stubbed his toe, and he yelled, and he screamed, and he bawled his eyes out. He went back into his hut, and he said, "I don't know what I'm supposed to do. My toe's killing me." He looks to his wife, and she says, "Sokatoa." He said, "What?" She said, "Sokatoa." She was telling him to soak your toe. Huh? That's how this is pronounced. When you pronounce it like you're just a complete moron. So-ka-to-a. Sokatoa. What this acronym is for, SOH, sine, opposite leg, hypotenuse. Cosine, adjacent leg, hypotenuse. Tangent, opposite leg, adjacent leg. That's what that's for. It's a mnemonic device. To solve a triangle, it's a definition. It means to find the measures of all the sides and all the angles. Every triangle has the lengths, or has three sides, so that's three lengths, and it has three angles. So you'd find the measures of those three angles. Angle of depression and angle of elevation. Let me draw for you a nice little drawing. That's the ground. And let's say we got a building on top of the ground. Got to have a door. Maybe a couple windows. An angle of depression starts at a horizontal and depresses. Depresses means to go down. So let's say that there's a dude on top of this building, a one-armed dude. And he sees down here on the ground a flag. And the problem says the angle of depression from the dude to the flag, 20 degrees. Well, you take his line of sight. I made it dashed because it's not really there. That's a horizontal. And his line of sight to the flag might be like so. This part right here is the angle of depression. If it says an angle of elevation, that starts at a horizontal and elevates. Notice both start at a horizontal, one depresses, one elevates. If it says that the angle of elevation from the flagpole to the dude is 20 degrees, that would go here. That's the angle of elevation. Both of them start at a horizontal. Both of them, no, that's not true. One of them depresses, one of them elevates. Depress means go down from the horizontal, elevate means to go up from the horizontal. But here's the good news. These horizontal lines are always parallel. And since they're parallel, we end up with two parallel lines in a transversal. This is all geometry stuff. If you get two parallel lines in a transversal, then a pair of alternate interior angles will be the same. So that means the angle of elevation and the angle of depression must have the same measure every time. All right, one more thing I want to go over with you, and then we'll do some examples. Important stuff, once again, from geometry. It's got to be emphasized. Inverse operations. So if I give you an operation and I want to know what its inverse is, you should be able to tell me. For example, addition. What is the inverse of addition? Well, it's subtraction. What's the inverse of subtraction? Addition. Multiplication is division. Division is multiplication. What about squaring? We pretend that square rooting is the inverse of that. It isn't really, but it's good enough for us in high school. Well, what is the inverse of sine? It is something called, and this is a great name, it's called sine inverse. Let me just get rid of this A. Sine and sine inverse are opposite operations. Cosine and cosine inverse are opposite operations. Tangent and tangent inverse are opposite operations. It's important to note that in this context, this -1, it is written as an exponent, but it does not mean an exponent. It does not mean to reciprocate it. It means the inverse of that trig function. So one more thing I got to go over, and that is, let's say that we have 4 sine of 4 degrees equals, let's not do that. Say we have x sine of alpha equals y. Couple questions. What mathematical operation connects the x and the sine? Take a guess. Louder. It's multiplication. If they're attached by multiplication, what is the inverse operation you would use to unattach it? Well, you would use division if you wanted to unattach it. Follow-up question. How is sine and alpha attached to each other? It is not multiplication. It is not division. It is not addition. It is not subtraction. It's attached by the trig function. In this case, it's attached by sine. If you want to unattach it, you have to do sine inverse to both sides of the equation. Let's do an example. The directions: solve each triangle. That means find all 3 measures of sides and all 3 measures of angles. Given the right triangle below, round angles to the nearest minute and sides to the nearest tenth. We are told that angle B is 42 degrees and 10 minutes. We are told side A is 9. So we know what angle C is. It's 90. We know that A is 9 and measure of angle B is 42 degrees and 10 minutes. So what are we missing? Side B, side C, and angle A. There's a theorem in geometry, I believe it's called the complement theorem, that says in any right triangle, if you add the two acute angles together, you will always get 90 degrees. So if we subtract 42 degrees and 10 minutes from both sides, we get 47 degrees, 50 minutes. How do I get that? let me explain that as well. Some of the details in this assignment can be complicated. If we're trying to subtract 47 degrees and 50 minutes from this, we're taking 50 away from 0, which we can't do. So we have to borrow. So we change the 90 to an 89. That's how we get 89 minus 47. Pardon me, I wrote that down wrong. It's supposed to be subtracting 4210. So I'm subtracting this from both sides. 42 subtracted from 89. Oh, I got a cramp in my foot. It hurts so bad. Must push on. That's how the 47 comes in. Boy, that cramp hurts. If you borrowed 1 from the 89, that means you're taking 1 degree away from it, and you're going to change that 1 degree into minutes. Well, how many minutes are there in 1 degree? There's 60. So now we're taking 10 away from 60, and we get 50. That's why this is 47 degrees and 50 minutes. Next, let's say we want to find the measure of angle, or of side B. Pick one of your acute angles. I'm going to choose B. You could also choose A. If we want to know what side B is, that's a variable. I have to pick another side that I know the length of, such as 9. Well, what trig function is this? It's going to be tangent. Why is it tangent? B is the opposite leg. A is the adjacent leg. Tangent of an angle is the opposite leg, B, over the adjacent leg of 9. Trying to get B by itself, we would multiply both sides of the equation by 9. It's going to cancel the 9's on the right. So on the left, we get 9 tangent of 42 degrees, 10 minutes, equals B. You must write that out. Put that into your calculator, and you're going to get 8.151. The directions said sides to the nearest tenth, so it's 8.2. Question: how do you put 42 degrees and 10 minutes into your calculator? I don't have my calculator with me, but I believe there's a button on your so you hit the tangent button, then you hit 42. I believe there's a button on your calculator that says angle. Find that button, find the degree symbol, hit the button again that says angle, and then type in 10, and then the minutes, and hit enter. You should get 8.2. If what I'm telling you is not right, ask me when you get to school, and I'll show you how to use your calculator. Please keep in mind that 8.2 is rounded. We do not want to use rounded numbers to find answers unless we have to. We don't have to. To find C, we're going to use angle B, the adjacent leg, and the hypotenuse. That's cosine. So we're going to have cosine 42 degrees, 10 minutes equals the adjacent leg of 9 over the hypotenuse of C. To solve the equation, we want to get the variable off of the fraction, so we're going to multiply both sides of the equation by C. On the right, C's cancel. On the left, we get C times cosine of 42 degrees, 10 minutes equals 9. To get C by itself, we divide both sides by cosine of 42 degrees and 10 minutes. That's going to give us C equals 9 divided by cosine of 42 degrees and 10 minutes. Put this into your calculator, and this is about 12.1. Supposed to solve the triangle. We've done it because we found the missing measures. We write them down here on the appropriate blanks. C is about 12.1. B is about 8.2. Measure of angle A is 47 degrees, 50 minutes. Make sure I rounded according to the directions. I did. Moving on to the next one. Same directions. This time A is 21 and C is 30. Something you don't want to lose track of in all this right triangle stuff is the Pythagorean theorem. Pythagorean theorem says if you have a right triangle, which we do, you can square each leg and add them together, and it will always equal the hypotenuse squared. Since we have two sides of the triangle and neither are rounded, we can use the Pythagorean theorem. 21 squared plus b squared equals 30 squared. 21 squared is 441. 30 squared is 900. That makes b squared 459. 459 is not a perfect square. The direction said to round to the nearest tenth. So b is going to be about plus or minus 21.4. This is the length of a side of a triangle. At this point in your math career, assume it's going to be positive. In the near future, we will not be able to assume such things. That's right. In the near future, we're going to have negative lengths. Amazing, isn't it? So if b is about 21.4, we do not want to use that rounded number to find anything else in the triangle. Let's say we want to find angle b next. The two sides that we have that are not rounded are the adjacent leg and the hypotenuse. That is cosine. Cosine of angle b equals the adjacent leg over the hypotenuse. Now we have to try to get b by itself. How are we going to do such things? We have to figure out how to unattach cosine and b. They are attached by cosine. So to unattach it, give myself a little bit of space here, we are going to do cosine inverse to both sides of the equation. On the left, inverse operations cancel. So we end up with b equals, on the right we get cosine inverse of 21 over 30. This is the exact answer. The directions ask for a rounded answer. So I put that in my calculator. You hit second cosine, 21 divided by 30, close your parentheses and enter. You're going to get some kind of a decimal. If you go and hit the math button, I believe there's a thing that says, like an arrow pointing to the right, to degrees, minutes and seconds. Select that, and it's going to change it to 45 degrees, 34 seconds. If it doesn't do that in your calculator, when you get your decimal, 45 point whatever, 5 something, subtract the whole number, so you just have the decimal, then multiply the decimal by 60, and that will get it into minutes. I got 45 degrees, 34 minutes. So what are we missing now? We are missing angle A. Sometimes I contradict myself. Here's one of those times. If you know two angles of the triangle, find the third using that complement theorem. Do not, I mean you can, that's not wrong. You don't need to use a trig function to find this missing angle. We are just going to take our two complementary angles, measure of angle A, plus our other complementary angle together equals 90 degrees. Subtract 45, 34 from both sides, and you get the measure of angle A is 44 degrees and 26 seconds. How do you find the answer that fast? Here's what I always do. You know, I'm not great with numbers. I make sure my degrees add up to 89 degrees. Then I make sure that my seconds, or my minutes rather, add up to my degrees add up to 89, and my minutes add up to 60. Because 60 minutes is 1 full degree. This is the same as 90 degrees. So that's what I'm trying to accomplish when I do that. If it doesn't make sense, ask me in class and I will try my best to explain it. Write the answers in the appropriate spots. 21.4, 44 degrees, 26 minute. And let's see, measure of angle B We got 45 degrees, 34 minutes. Number 3, whoa, we are out of room here. That's unfortunate. Measure of angle B is 30 degrees. Side B is 7. Here's why it's not so unfortunate. If one of your angles is 30 and the other one's 90, this one has to be 60. That's a special right triangle. Boy, is it special. In a special right triangle, short leg, whatever that is, in this case it is B. Whatever's opposite of 90, which is the hypotenuse, is that times 2. So that means C is going to be 14. Whatever is the short leg is, the long leg, which is opposite 60, is that times the square root of 3. That's going to make this 7 times the square root of 3. Special right triangles are immensely important, and hopefully you have learned that in the past. If that doesn't make sense, come see me, and I'll spend some more time on it. Last problem. This one is a rough one. A flagpole, 40 feet high, stands on top of Riley's Regent building. So I'm going to draw the ground. I'm going to draw the Riley building. Going to draw a flagpole on top of it. That flagpole is 40 feet high. That's not from the ground, that's from the top of the building. So first sentence, got it. From a point P in front of Bailey's Boutique. Well, I don't know if Bailey's Boutique is taller or smaller than Riley's Regent store. I'll just put a B here. I could make it taller or shorter. At this point, I don't know. But I do know there's a point right in front of it called P. From a point P in front of Bailey's Boutique, the angle of elevation to the top of the pole is 55 degrees. So if I draw a segment to the top of the pole, the angle of elevation starts at a horizontal and elevates is 55 degrees. The angle of elevation to the bottom of the pole was 47 degrees. So from P again to the bottom of the pole, that angle of elevation, 47 degrees. To the nearest foot, how high is Riley's Regent building? Well, let's call that Y. Always encourage you to box in the question. So I don't know if you recognize what's happening here, but we got a bit of a problem. We are trying to find the length of Y in a triangle which we don't know the length of any side. If we try to use the big triangle, we don't know the length of any side in that either. So we are hurting in either case. What do both of those triangles have in common? This bottom leg, they both have that in common. We'll call that X. So check this out. In the red triangle, I could say tangent of 47 degrees equals the opposite leg over the adjacent leg. That's what tangent is, opposite leg over adjacent leg. Now I can't solve this equation. There's two variables. But what I could do is I could get Y by itself by multiplying both sides by X. It's the best I can do. That's what Y is. X tangent of 47. If I knew what X was, I'd put it in and I would be able to finish this. If I look at the big triangle, like so, I'm going to call that whole length over there Y plus 40. Makes sense because there's 40 from here to here, and then Y from here to here. Add those together, that's the segment addition postulate from geometry, and you get that the whole length is Y plus 40. So that big blue triangle, I can say tangent of 55 degrees equals the opposite leg of y plus 40 over the adjacent leg of x. I still can't solve it because there's two variables. But here's what I can do. Using the substitution property, I can replace y in that red equation with x tangent of 47 degrees. Well, how does that help? It helps because then I have an equation that has only one type of variable in it. One equation and one variable, I should be able to solve it. So this is going to get complicated if it hasn't already. Step 1, draw the picture. Step 2, write an equation. Step 3, make another equation. Step 4, substitute one equation into the other. Now I'm going to keep trying to solve this until I get x by itself. I want to make it so that I don't have x in a fraction. I'm going to multiply both sides by x. On the right side, that would cause the x in the denominator to not be there anymore, because x divided by x is 1. Still having trouble solving this. I want to get all the x's, the terms with x's, on the same side of the equation, and both of these terms have x's. So I'm going to subtract both sides of the equation by x tangent of 47 degrees. Sometimes my 7s start looking like 2's. Now I have my x's on the same side, and it's this next step that often blows people's minds. To solve the equation, I have to get x by itself. And the problem is I have x in two different terms, and they're not like terms. They're not like terms because the angles are different angles. So what do? I factor. What type of factoring? The easiest type of factoring. I factor out the greatest common factor in these two terms. The first term has a factor of x and tangent of 55. Second term has a factor of x and tangent of 47. The GCF here is x. If you factor that out to the front, let me change the way I write my grouping symbols. We're going to get x times tangent of 55 degrees minus tangent of 47 degrees. The reason that I use brackets is just visually it's easier to see than using double parentheses. Now to get x by itself, it's actually pretty simple. We just divide by both sides by that mess in the brackets. We're going to have 40 divided by tangent of 55 degrees minus tangent of 47 degrees. Put that in your calculator, you're going to get that x is about 112.429. Couple of things. The direction set around to the nearest foot. I'm not finished with the problem. So I'm scared of rounding things. I don't know if you can tell, but right now my voice is quivering a little bit. That's how scared I am. So I'm going to round to more decimal places than it asked me to, so when I get to my final answer, hopefully I haven't rounded too much. Second of all, take a moment and put this in your calculator. If you don't get the right answer, here's why. The denominator is more than one term, so you've got to put it in parentheses. See if we answered the question, even though I've already told you we haven't. To the nearest foot, how high is the Riley's regent? Riley's regent is y. We don't know what y is. We found x. Step 5. We're going to take the equation x tangent of 47 degrees and replace x with 112.429. Put that in your little calculator and smoke it, and you're going to get 120.565 is y. At this point, we can answer the question clearly. To the nearest foot, how high is Riley regent? Riley regent is about 121 feet tall. That concludes the lesson. Best of luck.